Chapter 2, Section 1 is using first derivatives to find maximum and minimum values and sketch graphs. Okay, before we do that, we need to clear up some vocabulary and talk about some concepts. I have a graph here that we're going to use for our example. And the first thing we're going to discuss will be intervals on which this graph is increasing. And we could tell this about functions using our first derivatives without even graphing them, which is interesting. So increasing means that as my x values increase, what's the behavior of the y values? If they're getting larger, then we're considered to be increasing. So this is occurring from negative infinity until we get to 1, 2, 3, 4, negative 5. It's occurring between x is negative 3 and 0. It's also occurring between x is 2 and 4. So what increasing then are intervals on which as x increases, y also increases, means your graph's going uphill. The derivative evaluated at those x values will be positive, because if you think about drawing tangent lines on any of these intervals, they're all going uphill. They all have positive slopes. So here are those intervals. Now notice they're in parentheses, which means they're open intervals. The endpoints are not included. At the point of change, where you stop going uphill, you start going downhill, you're actually not doing either one of those things. So therefore, we're going to use the parentheses on our interval notation. So decreasing will be as I move from left to right, as my x's are increasing, what's the behavior of my y's? If they're getting smaller, then my graph is considered to be decreasing on those intervals. So in this particular picture, we're decreasing from negative 5 to negative 3. We're decreasing from 0 to 2, and then we're decreasing from 4 to infinity. And again, at the point of change, you're not doing either of them. So you're going to use parentheses and have open intervals here. Okay, so intervals on which x increases and the output values, the y's, decrease, you will be considered to be decreasing. At those places, the derivative evaluated for those x values will be negative, because if you think about it, when I draw any tangent lines on any of these intervals, they're going downhill. They've got negative slopes. Okay, let's talk about max and mins. A max is a high point or a high y value. A min's a low point or a low y value. So a relative max or a relative min means within an open interval of your graph, not the whole thing, there's going to be a point that will be higher than the rest or have a larger y value than the rest. That's considered to be a relative maximum. So on our particular picture, that happens here at negative 5, it happens at 0, it happens when x is equal to positive 4. So they're occurring at the x values. The relative minimum, or excuse me, maximum values themselves will be the y values. So at negative 5, the relative max would be 1. At 0, the relative max would be 3. And at 4, the relative max would be 1 again. Okay. Notice a relative max, you're increasing on the left, decreasing on the right, increasing on the left, decreasing on the right, increasing on the left, decreasing on the right, which we can use that to our advantage when we do first derivatives to help to locate these local max values. Now a local minimum value will be where on an open interval you're the lowest point. So you would be decreasing on one side and increasing on the other. In this particular picture we have two of them. On this open interval, our low point's here at x is negative 3, and the minimum value would be negative 2. Now on this open interval over here, the minimum point would be right there. So when x is 2, our local minimum value is 0. So as far as definitions go, a relative or a local max is a point at which the graph to the left of it is increasing and to the right of it would be decreasing. A local high point. Example, at x is negative 5, the local max is 1. At x is 0, the local max is 3. And then if I want to write it as an ordered pair, that local max is occurring at 4, 1 for the third one. Our relative or local minimum, a point at which the graph to the left is decreasing and the graph to the right is increasing. So it's a local low point. Example, when x is negative 3, the local minimum is y is negative 2. and when x is 2, the local min is y is 0. Again, these are occurring on small open intervals, not over the whole graph. Okay. So that brings us to absolute max and absolute mins. Now, an absolute maximum would be the highest point on the entire graph from negative infinity to infinity, or whatever your domain happens to begin and end at. So for our particular graph, we actually have an absolute maximum value. It's occurring right here at x is 0, and it would be, the absolute max would be 3, because to the left and to the right, we are falling in both directions. So they are decreasing without bound, which means, yeah, I have an absolute max, but in this particular graph, I'm not going to have an absolute minimum because both sides keep decreasing. It could be that your graph has neither. If this particular graph did not take a turn here and head down and just kept increasing without bound, then it would surpass this this y equals 3 at x is 0 and keep going for higher y values, and therefore it would not have an absolute maximum or an absolute minimum value. So the absolute max is going to be the highest point on the graph on the interval given, which, again, our interval was negative infinity to positive infinity. If you have a closed interval and you're just looking at a section of a graph and nothing beyond, then you're guaranteed to have an absolute max and an absolute min value, because you'd be working on a closed interval that begins and ends specifically somewhere. On our open interval graph from negative infinity to infinity, our absolute value was 0, 3. Absolute minimum is going to be the lowest point on the graph on the given interval, and for example, we said there was none in ours because we decreased without bound to the left and right. Now, critical values, I was saying we could use derivatives to help us find local max, local min. At the local max and local min points, we have tangent lines that have a slope of 0. In other words, your derivative is equal to 0 at those places. So if you find your first derivative and set it equal to 0, then you can find the x values that make that happen, which are potential local max, local min values, which is why we call them critical values. Now, the other place that they may happen is a place like this point where I have many tangent lines, so the derivative actually does not exist here. So we're looking for places where our derivative is 0 or it doesn't exist to narrow down where our local max, local min values are. And we're going to call those critical values. So value for which our function is equal to 0 or it doesn't exist. They are potential max minimum points on the graph. And again, just potential. They're not guaranteed. Okay, and right here is a definition. The first derivative test for relative extrema for any continuous function f that has exactly one critical value c that falls on your open interval. Again, you may have many open intervals and many different c's, but if you have one of them, your relative minimum, if your derivative is less than 0 on, and then
from C to B on the right hand side you're increasing, and I've got an easier description on the next page. You have a relative minimum if to the left hand side you're increasing and then to the right hand side you're decreasing, and you have neither if you are increasing on both sides or decreasing on both sides. Okay, so we're going to have part 2 where we do